Let's look at example 3.8. In 3.8 we have a beam with 4 forces acting on it, and it's asked for the beam to reduce the system of forces to an equivalent force couple system at a few different places. Here, first one we're going to do it here at A, then we're going to do it here at B. And then later we're going to figure out where's the one place where you can put it where it has no moment. We'll talk about that in a second. So part A. So at A, so let's look at the sum of the forces. What are the sum of the forces? Well, you have 150 going up plus 600 going down plus 100 going up plus 250 going down. So what is the net result of that? This is sum, sorry. There's a net force of 600 newtons going down. Okay, so for a system of forces to be equivalent, what do you have to have? You have to have the same tendency to translate and the same tendency to rotate. Well, the forces are going to be what makes it translate. So we know that we need to have 600 newtons. Our system needs to be 600 newtons. Now, when we move all that 600 newtons, so what do we have? We have this, we're going to write this as a kind of thing as we have this platform, and we're going to say, hey, there is just one force here of 600 newtons. Well, when we draw that one force there, we're giving up a certain amount of moment. So what moment is there? Well, the way we figure that out is we say, okay, what is the moment at A? Well, the moment at A is 150 is passes through A, so there's no moment, but then you have 600 times 1.6, and then minus 100 times 2.8, and then going to be plus 250 times, that's 50, times 4.8. So the moment at A is 1880. In which direction? Now you notice I picked the first one to be positive. There's no real rhyme or reason. I just figured one positive. I just being consistent that they're opposite. And so this one, it's in the direction of this. This is the one that's how I defined it positive. So what is that positive? That's in that direction. So therefore, over here I have 600 newtons pushing down and 1880 Newton meters rotating it about that axis. So that's part A. Okay, let's look at part B. Well, part B. So part B, we want to do the same thing, but at point B. So here, we'll draw this over here. We're going to have the same beam with the same little, right? But now we're going to put some amount of force here and some. So what is that force? Well, the translational force, again, it's the same. It has to be 600 because that has to stay constant. But what is that moment? That's going to be the different animal. So we're talking the moment at B is what? Well, the moment at B, you have 150 times 4.8, and then the minus 600 times 3.2, and you have plus 100 times, in that case, it's going to be 2. Right, so the moment at B turns out to be 1,000 Newton meters. And in which direction? Against we define that first one as positive, so it's in that direction. Okay, so this, therefore, we have to add in this moment of 1,000 Newton meters. And that is your equivalent at B. Okay, let's look at C. Part C asks for what is the equivalent single force or resultant. So how do you get, again, for a system of forces to be equivalent, what do you have to have? You have to have the same tendency to translate and same tendency to rotate. So your force, is going to be simply 600 newtons down, right? But if we're saying that we want to do this as a single force, well, that means there's no moment. So is that possible? Well, it is, but only in one select spot. You have to pick the right point along this beam. So what we're saying is you have this beam now, and we're going to go ahead and put a single force of 600 newtons at some distance. this is really poorly drawn scale-wise, x, that makes it equal to the same as the other system. Well, we can take either of our previous two answers. We can take this one right here, or we can take this one right here. Just for giggles, let's take the one at point A. So I can scroll this up a little bit. At A, the moment at A is 1880, right? And that is, if we're writing this as one single force, it's going to be 600 times the distance x. How far is it? We're trying to take the moment about this point right here, right? So this force 600 times this distance should give us that same moment, right? So therefore x ends up being 3.13 meters. You could do the same thing at B, right? The moment at B is 1,000, which is going to be 600 times. Now, if we want to keep x from this direction, we want to figure out what this distance is here, and that distance is the whole length of it minus x, right? So the length of the whole thing is 4.8 minus x, right? And so therefore, you can work that out, and you're going to find out that x is equal to, strangely enough, 3.13 meters. So you get the same answer on both ones, which is what you'd expect. You could actually even do it in a harder way. You could go through and you could say, okay, here's the original one. Here are my forces. What are the forces? I want to run in the same direction. There's this force. There's this force. There. Oops, sorry. I'm doing them backwards. But you could go through and add your forces, and you could pick a point here, take a moment at some point x, and then go through and figure out what all the moments are to equal 0. And you're going to find yet again the moment or the distance is 3.13.